Hello friends, so now we will just recapitulate Newton's third law and then we will step into problems. So Newton's third law. In simple words, if we say, it's simple action-reaction theorem. Like every force has equal and opposite reaction. Or in other words, suppose if a body A exerts force on body B and this force is of magnitude F. Force F on body B, then body B exerts force minus F on body A. This is body A and this is body B. By any means, this can be any force. It can be gravitational force, it can be force due to a string, or even if this body strikes on this body B. It can be any force, irrespective of the kind of force. If A is exerting a force F, force is a vector quantity, so we are noting it with a vector notation. So then that time B will exert a force minus F. And as you can see, this minus sign shows just that the direction is opposite, and since it's F and it's also F, so the magnitude is same. So that's why if A exerts force F on body B, then body B exerts force minus F on body A. Means the force exerted in the form of reaction will be equal in magnitude but opposite in direction. So this is as simple as this. Now we will just see in another form of example. Suppose there is a block kept on ground and there is a man and he is trying to pull this block. So you can see this is a block A which is being pulled by a man to this direction. So the man is holding the string and that string is tied to the block. So ultimately man is applying a force so that the block A can be dragged in this direction. So here this is one body, the man, this is the second body. So body 1 is exerting a force on body 2. This force can be F. Then using Newton's third law we can say that at the same time this block A is exerting a force minus F on the person. It should be. Now if I say you that since there is a one force F and another force minus F, so ultimately the system should be at rest. Net force cancels out, because if we add these two forces the summation will be 0. So how do we find that if a person is pulling a block, the block gets dragged? The person does not get dragged, rather the block gets dragged. So what is the physics in this? If we see in one way, we will see that this force F and this force minus F, the net force on the system cancels out. The mistake is that we cannot just cancel out these two forces, because in physics there is a word system and there is a word body. Now we have to understand this. problems are concerned, body is defined in physics as one object on which if any force F is applied, then all the points inside that object will have same acceleration A. So if there is any object in our surrounding, which you see that if any force F is applied on that, then each particle or you can say each molecule of that object possesses same acceleration A. Then that object is termed as body, a solid body in physics. So whenever you see the word body being mentioned in any problem, you should make out this picture in your mind, that this is if it is given that this is a body A, it means that no matter how many forces are applied on body A, the net force, maybe say F, if this is the net force, then acceleration of each particle of the body will have same acceleration A along that direction of force F. So this is body. But if we come to system, then say this is an object, this is another object, object A, object B. Now suppose a force F is applied on this, and the situation is such that these two objects move simultaneously with equal acceleration. It may happen. So at that time, we can say that this is an entire body, because acceleration of A is same as well as acceleration of B is same. It means all the particles of B and all the particles of A have same acceleration, and the direction will be along the direction of F. But it is also possible that A may move faster than B, because ultimately this entire phenomena will depend on the relative friction between A and B. So both objects move with same acceleration may happen, and both objects move with different acceleration may also happen. So in that case, we cannot term it as a body, rather it's a system. A system may consist of any number of bodies. So it's a system, not a body, because at instances the acceleration of all the particles of A may differ from the acceleration of all the particles of B. So this is termed as a system. So this is the definition of system and body. Now here, if we apply this concept here, then definitely we can say that this is a solid object. So whatever force is being applied through this string, the acceleration of each particle of the object will be same. So this is a body. This person can also be termed as a body. But this may be a body or may be a system. So depends on the condition. That if the string which we are using, if the length of the string do not change with time, because what will happen? You just imagine that you have tied a rope or a light string into a body and you are trying to pull it. When you will try to pull it, then definitely you can imagine that actually the person is applying force on a string, and then a string is applying a force on the object A, because these are contact forces, not field forces. So person A is standing here, object A is here. So person A cannot apply a force directly on A. He has to arrange a contact. So what is the contact? The contact is the string. So these are the minute things we have to keep in mind, because then we will able to solve the tricky problems. That we have to see that which object is in contact to which kind of force. So ultimately you can see from the picture that a person is applying force on a string, and a string is applying force on the object, and that force is F. So here the assumption is length of a string is constant. Our second assumption is that a string is light, it's massless. So, in that case, if the person applies a force on the string, there will be not, in practicality, there will be extension in its length, but for the time being, we will assume that the length of the string is not changing and it's massless. So, this force is being applied from the person on the string, and the string is applying a force on object A. Now, when we talk about the acceleration, because the doubt came out that if the entire force is zero, then how the objects, these two people, the person and the object are going to move. What's actually happening is that the person is applying a force on the string, so he's actually pulling the string, and then the string is applying a force F on object A. So here, using this assumption that the length of the string is constant, we can say that if person is applying a force F on the string, then F will apply the same force, then the string will apply the same force F on the object. Because if this is the string, what happens? If we tie an object here at the bottom of it and it is fixed, then this object suppose has mass m, so that because of gravity we will have a force mg downwards. Now if you have tied anything from a fixed ceiling, then you see that this object is not moving, its acceleration is 0, but there is a force mg acting on it. So who is actually balancing this force? There must be a force to balance mg, otherwise there will be a net force on the object and the object will face an acceleration. But from Newton's second law, if I have found that F net is equal to m into acceleration. So if mg, gravity is the only force because of the virtue of mass, then there should be acceleration. But there is no acceleration. You must have seen such examples in your day-to-day life that if you tie an object with a string from a fixed ceiling, then you see that that remains fixed. So ultimately there must be a force to balance gravity. So that force is actually your tension. Because then practically what happens, that if we just leave the string loosen, if we just untie this block, then you will see that this string will be like this. Not so tensed, not so elongated. But when we tie something, it gets totally straightened. Why? Because the molecules inside the string, these small molecules, they extend. They do not extend much, just to show the picture clearly. I am extending it to this much, just to show you that in practically what happens, that these lengths are being extended, so there is a tendency of any object in the world to remain at its most comfortable position, most normal position. So there will be a tendency in the string to gain its natural length. So that tendency creates tension, and from there we conclude that the direction of the tension should be away from the object, because when there is object tied here, object will try to pull it down and it will elongate it in downwards direction. So the tendency of the string will be to pull back, pull above this object, so the direction of tension will be upwards. So whenever if you find any string, then at the moment if you find any tension, then we have to take the tension away from the object. So the tension will be away from object. If this is clear, I can just rub it here. So suppose this is an object, this is a string, and this is another object, A and B. We are applying a force F1 on this object, and we are applying force F2 on this object. Then this object will pull the string this direction, this object will pull the string in this direction. The string will be elongated from both the ends. So what the tendency of the string will be? To pull this object in this direction and to pull this object in this direction. So you can see that tension is acting away from the object, away from the motion of object. When motion of object A is in positive x-axis, then tension is in negative x-axis. When object B has a motion in the negative x-axis, the tension is in positive x-axis. So the tension will always act away from the object. And another important point to note it down here is that in a continuous string, the tension will be uniform. When I will discuss pulley problems, then I will show it again later. But for the time being, we must note it down that in any string, the tendency of motion, the tendency to come back to their actual position, to their normal position, so that tendency will cause, since the tendency will be uniform, that will cause a uniform tension throughout. And this uniform tension, I can write down the fourth point here, tension uniform. In a continuous string. And this fourth property comes actually because it is massless. If it will be having mass in any problem, if it will be mentioned that the string has mass, then tension will not be uniform. So this point you have to note it down, that if it is massless, if it is given that it's a normal standard string, if nothing is mentioned in problem regarding its mass, then we have to assume it as a massless string, and then we can apply this property that the tension will be uniform in a continuous string. Suppose the string changes. Suppose there is another string and there is another object C here. So then this will have a tension T dash here. Here it will be T dash. So this will have T, the string changes at object A, and this string will have different tension. So for a continuous string, there will be same tension. So I hope Newton's third law is clear. This string part is clear. At last, if we come back to this problem, then now you yourself can make it out that this is the tension which actually acting on this object A. So this tension will pull the object and the object will move. At the same time, we will say that how this tension is going to help this person. So this person, when he is moving, he's actually when a person moves, he applies a friction force here. He pushes back, he tries to push back the ground, and it's the friction which helps him move further ahead. So this is the friction which is actually helping this person to move. If you want to get the elaboration of friction, you can consult the video lecture on basis of friction which we have designed. So for the time being, you have to take in consideration that there is actually friction which is helping this person to move, and then this person is facing a negative tension in the opposite direction. So ultimately, using second law, we can write that, move it here, that mass of the block A, MA, into its acceleration, that will be equal to F, which is actually the tension in the string. F being applied from the person, and that will be equal to the tension. And at the same time, mass of the person A will have a friction force helping him minus F. And since the string length is fixed, that's why object A and the mass and the person both will have same acceleration. Because you can imagine that had this length been varying, then acceleration could have been different. But since this length is fixed, the both ends have a fixed length, then the acceleration at any time of this object and this person cannot be different. It's not possible. Because if it would be different, then definitely the length will be varying, start variation. There will be variation in the length. But since there is no variation in the length, this is an assumption. And all the problems which we are going to solve in Newton's law up to your level, we have to take into consideration that the length is not varying. And since the length is not varying, not changing with time, at any moment of time, the acceleration of this object A and the acceleration of the person, or any other case which we are going to solve later, both will have the same acceleration. So that's why I have used this acceleration A and A here both. So ultimately it drops down to two variables. This is one variable, this is another variable. It's a linear equation. We can solve this equation simultaneously and ultimately we will get the answer. So this is the actual physics which is taking into consideration the entire picture here. So from the next lecture we will actually deal into how to solve multiple object problems of Newton's law.